Okay, we're recording right now. Okay, you guys ready? So last time we gave some motivating examples of estimation, optimal estimation, covered some fundamentals rather very quickly in probability theory. And then we derived the linear least squares and the weighted least squares estimators. We talked about the maximum likelihood estimation, MLE, and the maximum a posteriori estimation map, also rather quickly. Now we'll talk about the recursive minimum variance estimator. This is important to understand the Kalman filter derivation. It's basically the derivation, and then we will adapt it a little bit to get to the Kalman filter. So to remind you, last time when we talked about the linear least squares, LLS, and the weighted least squares, estimators, the expression for the estimator x hat, it required matrix inversion. So the larger the matrix H, something is stuck, it's not moving. Now it's moving. Yeah. So the larger the matrix H, then the computation is going to be more expensive. So, but what if H is, so the measurement model, so yeah, exactly. So we're saying that the observations or measurements are nothing but a linear combination of the states that we're gonna after to estimate. But what if we're getting these measurements y sequentially, one at a time? Wouldn't it be nice if we can just start with a rough estimate of x and then update or refine the estimate as we get more measurements? So like you do, it's like if you go to the simple example we mentioned about measuring the resistance of a resistor multiple times and then generating an estimate of the resistance. Yeah, that's a simple example. Yeah, we're estimating a constant, the resistance in this case. So we need to collect. No. This an example. It's like you're getting these measurements, not all at once, not all at once. So if I measure the resistance 10 times, I need to collect all these measurements and then do the matrix inversion, do the pseudo-inverse to get the final estimate of the resistance. But here I'm saying no. We get one resistance measurement from one multimeter, and then we generate our initial estimate of the resistance. And we get another measurement, then we refine the estimate of the resistance, and so on. Exactly. We update as we get these measurements one at a time instead of waiting until all of them accumulate. So that's the point of recursive estimators. So now assume we have the same measurement model, but except now I'm using a subscript k. So here x is still a constant. It could be a scalar, it could be a vector in this case, still a constant. And here y is our measurements, but now they come in as samples in time. And that's why the index k. Here we're allowing h to vary with time. So instead of saying that this model is time invariant, it could be time varying. Yeah, h can here I'm simplifying the problem, but then later we're gonna allow it to change, to grow. Yes, you can have different values of x states with time. Here v is white noise, and what white noise means is that it has zero mean, and the covariance matrix is given at some point in time. But what does this statement tell us? The expected value of v sub k, v sub j is zero. Basically, it says that if you consider two different instances of time, then the noise is uncorrelated between these two instances of time. This is by definition what white noise means. Okay, so assume and this is a big assumption, but it will work out nicely. Assume that our estimator takes this form. We take the previous estimate and we add to it a correction term. And the correction term is a function of the residual, basically the measurement minus the expected measurement. Okay, so let me explain that and put it formally. So y hat is nothing but h sub k times the previous estimate, x hat of k minus 1. So we subtract that from the measurement y sub k and we get the residual, this difference. And we're going to assume that we take a linear combination of this vector, and that's our correction term. And the linear combination is defined by this K matrix, which is called the gain matrix. And later we're going to call it the Kalman gain matrix. So just if you're dead on, if your estimate, this is a constant, right? X. If you're right on from the first time you estimated correctly, then your residual is going to be 0. So at is going to be 0. So basically you get the correction term is 0. So you're going to get that x hat of k equals x hat of k minus 1. Yeah. So it's simple. Yeah. Or but usually what happens here, you start with some rough estimate, and then with time you converge to the, after a bunch of samples, you converge to the final. So we're assuming that the correction term is linear, is a linear function of the residual, if you want to look at it this way. But we don't know what k is. So next step is to calculate k. But let's see. So it turns out that the above expression, the boxed expression here, this estimator is unbiased regardless of what k is, which is nice. And this holds true if the mean of the noise is 0 and if this expectation is 0. And this expectation, we can read it as the expected value of the estimation error at the k minus 1 instant. Because this is the true value, and this is the estimated value at k minus 1, the k minus 1 sample. So this is nothing but the expected value of the estimation error at the k minus 1 sample. Notice that this boxed equation represents a linear system that is put in state space form. And our state vector is the x hat. And our inputs are actually the measurements because they are known. We know what the value for the measurements are. So in this case, can you figure out what the state transition matrix is? And like if we have a continuous time, I don't know if this rings a bell, x dot equals ax plus bu. Does this ring a bell? This is the state space. Yeah, exactly. This is a discretized version of this form, but here A is called the state transition matrix. And if you discretize this this equation, you get x of k equals some discretized x of k minus 1 plus blah 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 b. So this is the state transition matrix. So what is the state transition matrix in this case? It's what's multiplying the x hat. So this is the discrete version of an equation like this, the discretized version, and this is the state transition matrix, and this is the known matrix. Well, it's not known until now, but it's a constant, or it's a deterministic quantity, not stochastic quantity, that's multiplying our input. Our input in this case to this estimator. So this estimator takes as an input the observations or the measurements y sub k. Okay, so we have the form of our estimator, but we don't know what k is, and we still haven't talked about the optimality criterion. So the optimality criterion here, we want to find our estimate is the estimate that minimizes the cost function j, and the cost function here is nothing but the expected value of the norm of this vector here. And this vector is the estimation error. Okay. So I rewrote it here. Notice that if you expand this norm, then you get the expected value of the first term in that estimation error vector squared, plus the second squared, and so on. These are nothing but the variances of the estimation error. Okay, so that's why I call this the minimum variance criterion. Notice that this can be expressed as the trace of P, where P is the covariance, is the estimation error covariance matrix. So if P is defined this way, then it's a covariance matrix, and it's the covariance matrix of the estimation error. So this matrix is going to be, it's a covariance matrix, so it will be symmetric. Yeah, but it might not be diagonal. Yeah, then yeah, yes, but so here it's just no. If you look at if you have any, let me write here. If you have some random variable, call it x. Oh, no, call it v. So expected value of v transpose is by definition the covariance matrix. And this will be, let's say v is some vector that has two elements, v1 and v2. Okay, so this matrix is going to be nothing but the expected value. So I'm going to put the expected value of this matrix on, maybe not, let's not do that. Expected value, if you expand this, this is v, if you multiply v times v transpose, you get v1, v1, yeah, v1 or v2, v1, and here v1, v2, 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 and you take the expected value of that here to get the expected value of v1 squared, expected value of v2 squared. That's the diagonal elements. And here you get the expected value of v1, v2, and expected value of v1, v2 here in this example. So it's a symmetric matrix. So these are the variances of this random vector v, the diagonal elements. So we could say that the expected value of v transpose v is nothing but the expected value of v1 squared plus v2 squared, right? So basically, we're taking the expected value of the diagonal elements and summing them together. So that's the trace. That's the trace of this big matrix, the trace of the expected value of v transpose, which is the covariance matrix. Just simple, really. The norm is nothing but the trace of this big matrix. The norm of this random variable here, the norm of v is nothing but the trace of this matrix. V transpose v is just a scalar value. It's a norm. You mean v transpose? Oh yeah, the expected value of v transpose v is nothing but the norm. It's the expected value of v1 squared plus v2 squared, which is a scalar value. So v1 and v2 are the elements of this vector v. Well, it's I just showed you in the simple example. This is what we define. This is what we choose as our cost function that we want to minimize. That's all. So we choose in this case the estimation error, the norm of the estimation error, the expected value of that norm, and then that's nothing but the trace of the covariance matrix of the estimation error. Flip. It's just two equivalent ways of looking at it. But it's, yeah, I'm not gonna say any more than that. VV transpose is gonna be a 2x2 matrix, right? Because our vector V is 2x1. So then, but we want the expected value of that because it's a random variable. So then the expected value of the diagonal elements is, it gives us the variances of the individual elements V1 and V2. So let's say our cost function is going to be the sum of that, the diagonal elements. The sum of the diagonal elements means the trace of that covariance matrix. Here, this is a scalar. This is some vector. Let's call x minus x hat just for now, V. So this is V transpose V, which should be a scalar, which is what we want from our cost function. But then this is the same as the trace of that big matrix. That's what I'm saying. That's the only thing I'm saying here. Well, to be more specific, it's the correlation. Here we use covariance. Here we call this covariance, right? The covariance of the estimation, because there's an assumption that the expected value, we already said it, that our estimator is going to be unbiased. So the expected value of the estimation error is going to be 0. That's why that's why you could call P either covariance matrix or correlation matrix. So we spend a lot of time on this slide. Let's move on and let's focus on the big picture. And then these little small details, if you go back maybe to the slides from the previous week, you can figure out why I'm calling them the way I'm calling them, these variables. So now it can be easily shown that the covariance matrix takes this expression. And this expression holds true only if the estimation error at the k minus 1 sample and the noise V are uncorrelated. So this is what the statement means. The expected value equals 0 in this case basically means that our estimation error using the estimate from the previous sample and the noise, the measurement noise, they are uncorrelated. Then if that's the case, then we get this expression. And this expression, you can derive it if you remember what we talked about in last week. So last week, well, here, let me remind you of the equation from the expression from the previous slide. This is the expression for our estimator. And you can see the state transition matrix in green. Now, if we multiply by -1 and add x, we get this expression. So if this is the random variable that I have, x minus x hat sub k, and I want to find the covariance matrix for this random variable, which is the estimation error. And here, the matrix in green and purple, these are known values, deterministic values. Then we use the rules from the previous lecture. What would be the individual covariance of this term by itself? So in the previous lecture, we said that if we have some random variable y equals hx, then the covariance of y, the autocovariance, y with itself, is nothing but h covariance of x, autocovariance of x times h transpose. So here the covariance autocovariance of this term is going to be k times the covariance of v, but the autocovariance of v, we called it r. So k R K transpose. And remember, we talked, so this is our random variable here, the estimation error, is nothing but the superposition of this term and this term. We know how to find the individual autocovariance for each term, but then let's remember from last lecture, we said that if we have a sum of two random variables, x plus y, then the covariance of x plus y, the autocovariance, is nothing but the autocovariance of x plus the autocovariance of y, plus we have the cross terms. X, y transpose. But if we assume that x and y are uncorrelated, then these terms go to 0. So here we're going to do something similar. If we assume that the this term, the estimation error using the previous estimate at the k-1 sample, and the noise, the measurement noise, is uncorrelated, which is what we say here, then eventually we get to this expression. So I just showed you how we got this term, which is nothing but this term. And now here, this is similar. You take this matrix times the P matrix, or the PK minus 1. This is the expected value of x minus x hat sub k minus 1 times x minus x hat sub k minus 1 transpose. That's what we call P sub k minus 1. So P sub k minus 1 is nothing but the estimation error covariance calculated using x hat sub k minus 1. Okay, why am I doing this? Going through the little details, because if I give you just the equation, then you might not follow through. Or if you attempt to derive the Kalman filter yourself, you're not going to be able to do that. So these little details, little tools, I would say, would help you derive it. It might be too much, I realized, because half of you just checking their phones. But let's then, from now on, let's just try to focus on the big picture without going into the little details as much as possible. Okay, so remember our optimality criterion. We want to minimize this objective function, which is the estimation error, the norm of the estimation error. It can be shown, and I'm giving you the reference if you want to see the details. It can be easily shown in reference 3 that the best estimate is the expected value of x of k given all previous measurements up till the kth measurement. Okay, so now we're not going to go through the derivation. If you're interested, you can go to reference 3, but it's easy. It's not straightforward. Now I want to show you an alternative notation. Instead of writing y1 comma y2, we're going to just use capital letter y from 1 to k. Okay, and this is also another alternative representation. It means x of hat of k given k measurements, or given the measurements from y1 until y sub k. Okay, so really our estimate is nothing but the this guy. This is what we're after. Oh, and notice if I write this, y from 1 till k minus 1, or this expression, it means it's the expected value given all measurements up till the k minus 1 measurement. So it's important to give you this notation now for the upcoming slides. We gave you the form of the estimator. We know that the estimator is the expected value of x given all previous measurements, but we don't know what k is. So how do we find k? So it turns out, and again, it can be shown, I'm giving you the reference as well, if you want to see the details, it can be shown that minimizing the objective function can be achieved by minimizing k. And it turns out that this objective function as a function of k is some nice function, quadratic function, convex. We could just take the derivative with respect to k and set it to 0, and then solve for the optimal gain, k, resulting in this expression for k. So great, now we have the form for our estimator. Okay, is some previous value plus the correction term that is a function of the residual. And now we have an expression for k. Notice that the expression for k uses the covariance matrix. That's why we defined it earlier and talked about it, spent some time talking about it. And also it uses h, which is in our measurement model. And it uses r, which is the expected value of v transpose. This is the covariance of the noise, covariance matrix. I mean, if you think about it, you can't, if you have p as identity, you can have in certain cases h transpose to be rank deficient. So you cannot invert h transpose by itself. But notice here, there's an inverse, but the inversion takes place after adding this positive definite matrix. So this compensates for the rank deficiency that might be the case in this matrix. Okay, so let's summarize what recursive estimation is. And here, remember, we're estimating a constant, x. So you initialize by choosing values of the initial estimates, x naught, and the initial covariance matrix. So you need to give them initial values. And then for k, 1, 2, etc., do the following. When you obtain the measurement y sub k, we already know that the measurement model is hx plus some white noise. So when you obtain y of k, just update the following equations in order of the Kalman gain, and then the estimate, get the estimate x hat, and then you need to update the covariance matrix. So you need to do them in this order. So now we've prescribed an algorithm. You can simply in MATLAB code it and do a loop, and it will run this recursive estimation. Oh, finally, Kalman filter. Okay, building on the previous recursive estimator, assume that x is not necessarily now a constant, and it is a random variable itself. It can have a certain model of how it propagates with time as well. So what we're going to do for now is that we're going to replace x in our measurement model with x sub k. Okay. In addition to this model, which is, we also called it the likelihood function, by the way, which is this model here. We called it it has a certain PDF, f of y given x. We have another model. So now, not only we have a measurement model, we have a measurement model and a state model. So the state model tells us how x of k can be found given the previous state. It just propagates the states, the previous state to the using a transition matrix to the current state. So this is what we will assume on our. Now, you might have a propagation model that propagates previous x to the current x that is nonlinear. In this case, I'm showing you a linear model, linear in state space form. So f, b, and u. So f and b are known matrices. Okay, x is our state in this case, and u could be an input. Could be, for example, steering angle or throttle setting, depending on the system you're dealing with. And w is something to quantify, maybe the modeling inaccuracies in our model, or it could be an external disturbance. But we will assume that this w here is a white noise process. So W and V are white noise processes, and we're going to assume that they are independent. The W and V are independent, so meaning that they're uncorrelated. So if you take the cross covariance, it's going to be 0 between W and V. And we're going to call the covariance of W, the process or state model disturbance, we're going to call it Q. And we're also going to assume that W is uncorrelated to this vector here, x minus x bar. Now, why am I telling you this? That's in case, God forbid, you want to derive the Kalman filter yourself. So these are the hidden assumptions that you need to have in order to get to the result, the final result. Wow, we have a model of how x propagates, evolves with time, and it depends on the known quantities f, b, and u. X is the previous state, w is some disturbance. Can you find, given this model, can you find what x bar sub k is? Meaning, can you find the expected value of x sub k? So remember, the expectation operator is a linear operator. So we have to take the expected value of this term plus the expected value of this term plus the expected value of this term. The expected value of the noise is, no, expected value, it's white noise. So the expected value of the disturbance, W, is 0. What is the expected value of this term, B times U? It is B times U. Why? Because there's nothing stochastic about this term. It's all deterministic quantities. It's again, it's like I tell you the example that I said last week. If I tell you this this pen has an exact value of 10, then what is its expected length? Then you say 10. Okay, so and then what is the expected value of f times x? F is deterministic, so it's just like a constant. So f times x bar sub k minus 1. So this is the expression of x bar. But not only that, I also want you to find the covariance of x sub k, the autocovariance of x sub k. And the covariance, notice here, it's a function of f and the covariance of x sub k, the autocovariance of x sub k minus 1. And it depends on the covariance of w. The autocovariance of w is q. So why there's no dependence? If we want to calculate the autocovariance of x sub k, why is it independent from b times u? Because b times u is a deterministic quantity. So it's like saying, again, that I have a pen with a length 10 centimeters exactly. What is the variance on its length? There's no variance, it's 0. The variance is 0. So this is the same. The covariance, the autocovariance of BU is 0 because it's deterministic. All right, I colored these equations in purple because in the following slide we will use the same expression, but we slightly change. Instead of x bar, we'll use x hat. So remember these expressions as much as you can, because they will appear in the following slide. Okay, if W is Gaussian noise, and this is an exercise that we've done in last lecture, if W is Gaussian noise, then what would be the distribution of this random variable, x given x sub k minus 1? That is, what is the probability density function of x given x of k given x of k minus 1? So in order to answer this, I'm telling you here that we are given x sub k minus 1. So now, not only this is deterministic, but now this is also deterministic because it's given. This is deterministic, this is deterministic, and this is the only stochastic variable in this expression. So it's going to be, if we assume that W is Gaussian, then this PDF is going to be also Gaussian, but instead of it being 0 mean, it will be shifted by this much. and it would have the covariance of W. We've done this exercise in the previous lecture. Okay, so we also want to assume that the initial state is Gaussian, x sub 0. Estimation of x sub k, given all the previous assumptions and the fact that we have now two models, a state and a measurement model, and that both of the models are linear. Okay, that's that problem is called the problem that the Kalman filter solves. Estimation of x sub k given these assumptions. So you can think of it as fusing information from two models, the measurement model and the prediction model. The state model, it helps me predict what's coming in the future if I give you the present state. So we're fusing knowledge of these two together. So the Kalman filter is actually a special case, and the special case is that we have a linear state model with additive white noise to a bigger category of problems called optimal filter. So the measurement model and state model, they could be nonlinear. So maybe you could choose to linearize them and then use the Kalman filter, or use something called the particle filter. We're not going to talk about that. Okay, I'm going to repeat, which is important, the major result that you can code the recursive estimation and then compare it to the Kalman filter. You initialize, and then you have a measurement model. And then here we assume that x is a constant. And then we just update the Kalman gain, k. We have an expression for that. And then we update our estimate, x hat sub k. And then we update the covariance matrix P. So what if we want to use this as a special case? What if we put k here? But still, we know that x is a constant. And I tell you, if x is a constant and we want to add to this measurement model, we want to add a state model. What will be that state model? Remember, a state model gives you the value of x of k given the previous value, x sub k minus 1. So if I tell you ahead of time, this is a special case where x is a constant. Exactly. So you could say just, okay, this is my state model. X of k just equals x of k minus 1. X does not change. That's basically saying that x does not change with time. So this is just the identity here. The state transition is the identity. Okay, we already know this stuff. And notice that what I put in bold here, if we go to the Kalman filter, let's see what happens. The Kalman filter is exactly as the recursive estimation. You follow these steps, except what's in boldface on the left side of the screen is now in purple, and we slightly abuse the notation. So now instead of p sub k minus 1, we have p sub k given. So we have an estimate of the covariance given k minus 1 observation or measurements. And here we have, instead of x hat sub k minus 1, we have x hat k given k minus 1. So if you forget about this slight change in notation, so here, notice that this is my state model. Now, here what we have, x hat of k minus 1. Here we have a prediction of x hat given only k minus 1 measurements. Or you can think of it differently. How would we predict x hat given the previous state? We use the state model. So in the Kalman filter, in addition to the measurement model, which takes this form, we have a state model now. State model that tells us that xk equals some f xk minus 1 plus, okay? Whatever the rest of that expression is. So now x hat here is nothing but a prediction of the state. And how do we predict our state? It's through our state model. Yeah. So yeah, so here we had you can see it as here, this is a Kalman filter, but this with this state model. But now if we have a different state model with the matrix F not being the identity, and we have here another matrix B times an input U, okay? That's a different state model. So how do we get X based on the new state model? We use that, the expected value, or X bar, this is the expression here. Oop. Where is that? I went up too high, I think. Yeah, remember this is the generic form of our state model. Then we found an expression for X bar, and I put it in purple. That's the expected value of X sub k given the previous X. So we can use that expression to predict X sub k based on the previous value. And here we could use also this expression to predict the covariance. So that's what we do here. So this is the equation in purple in the previous slide. We use it here to predict X hat k given k minus 1. And also for P, k given k minus 1, it's, by the way, it's defined like this, and it's the same equation in the previous slide. So these predicted values, I call them predicted, are based on our knowledge of the state model. So this is the additional knowledge that we had originally when we were talking about the recursive estimator. We had only a measurement model, but now we have. So the fusion takes place here. So we have what you think the state should be, and then you have a measurement, and you see that the estimated measurement based on what you think the state is, you take the difference, you get the residual, and then you multiply it with a constant. This is the correction term, and this is how you fuse what your prediction with your measurement. Yes. Oh, imagine. Okay, so how do you? So let's think about the parameters of this problem. We have, maybe if we go to the previous slide, it'd be easier. The parameters that we have here, we have a measurement model. This is the guy. We have a state model. Okay. What do we know about the noise, the disturbance here, and the disturbance here? The covariance. The covariance of the noises are the covariance of the state model is the disturbance W is Q. So these are two of our parameters. So we have R and we have Q. We also have F and B in the state model, and we have H. So this is all the parameters that is needed to run our algorithm. Okay, so here, if your model sucks and you know it sucks, then Q must have much larger value than R. So this is basically how you weigh one more than another. So here we're saying we have a single system that is giving us the measurements and a model. Yes. So for example, the problem of occupant tracking in a building, because that's, I will go through an example now. We know that people walk with a constant speed, and we're roughly, most of the time, people are walking, not running. So we could use that information to come up with a state model of, if you give me the current position of an occupant, then you can project maybe after a second where the occupant will be. Okay. So that's your state model. I mean, but you don't know. Maybe the person is in a hurry. Maybe they need to go to the bathroom or whatever. So that's where the disturbance W captures that uncertainty in your model. And then you want to fuse. So if the uncertainty is large, you can put a large covariance matrix, or you think of the diagonal elements to be large. Okay, so let's show an example how you would go through this. You have a question? Okay, because I'm racing to get to the example. Okay. Because of lunch. Okay, so look at these smart people. Look at these smart people. Okay, I know these people, especially the first authors look smart. Anyways. So this is applying in this paper, we applied the Kalman filter to the occupant tracking problem. So now I'm going to show you how we have a measurement model now. I'll show you the measurement model and show you the derivation of the state model, and then how we applied the Kalman filter. Who's what? Nobody. So, okay, footstep location. So we need to come up with a state model that predicts how the upcoming occupant's location based knowledge of the occupant's current location. But let's see. Let X and Y denote the X and Y coordinates of the occupant's position. Okay. And the occupant most of the time moves with a constant acceleration, with zero acceleration. Let's see. Well, here initially, let's assume that the occupant moves with a constant acceleration, and then we will say it's zero mean. So, but initially now, for now, let's say that the occupant walks with a constant acceleration, and the acceleration vector has two components because this is a two-dimensional problem, the X component and the Y component. Then from physics 101, the kinematics equation of X and Y are as follows. So we have velocity in the X coordinate equals the initial velocity at the initial time plus the acceleration times the time step. Distance position equals the initial position plus velocity times time plus blah blah blah. This is equation, you know, and we repeat this. This is for the X coordinates, the equation 6a and 6b. We repeat these expressions for the Y coordinates. And this is the continuous time. These are just the kinematics in case you missed this, Dr. T. These are the, these are the kinematics equation of someone who's walking in a constant speed, in a constant acceleration. No, I made this. So this is a full derivation. So this is a full derivation. So, but it's simple. And I'm going to show you how it's done here. These are just, we have two, we have equations for the X coordinates and we have equations for the Y coordinates. So velocity in X at time T equals previous velocity plus accelerations times time difference, right? I don't know if this is clear. Can you see the, oh, you can. And the position equals current position plus velocity times time difference plus acceleration squared, acceleration times time difference squared by 2. Okay. Equation 6a and 6b, these are for the X coordinates. Same equations, we repeat them for the Y coordinate. Okay. So now we have 4 equations. For a sample data system, we can discretize these equations, okay, like this. So now this is the discretized version of these equations. Okay, let's collect these equations in a matrix form. So I'm going to call my state vector, I'm going to include in it position and velocity. And it makes sense. If you have someone walking at a constant speed, then it makes sense to assume that state velocity to include the state vector of the state model to include position and velocity. So we have velocity in x, position in x, velocity in y, position in y. And then we just rewrite these equations in matrix form. And guess what this matrix is? So this is x sub k minus 1. And this is the state transition matrix in our state model. Plus, we have some matrix that is multiplying acceleration. Okay. And now here's the trick. Assume that acceleration is 0, but have some white additive component. Basically, what we're saying is that the occupant, on average, does not accelerate or decelerate. On average, walks with a constant speed, but sometimes they might go faster or go slower, which is a fair assumption. Okay. And we assume that this W tilde, I call it, is white noise. But wait, now this acceleration is multiplied by this G matrix. So G is multiplying W tilde, and this becomes our disturbance W. So now guess what is the mean of this W? Well, maybe if you see, there's no guessing here. But the mean of this W is the expected value of W, is the expected value of basically is G times the expected value of W tilde, which is the expected value of W tilde is 0. So this is 0 mean. W is 0 mean. And also the covariance, if you follow the first lecture, the previous week, the covariance of something like this is nothing but G times the covariance of W tilde times G transpose. Okay, so now this becomes the covariance, our Q matrix. Remember Q matrix? This becomes our Q matrix. It's this expression. Okay, great. So now we have a simple or a simplified model. So now here Q, what I call Q tilde, is a design parameter. It basically says something about how uncertain we are about the acceleration. What is the uncertainty? What is the variance? So I'm gonna notice that it's a diagonal matrix. So basically, it's a diagonal matrix. We're gonna define the uncertainty in the acceleration in the x component and the y component. So for example, we could set the uncertainty to be the same. And the uncertainties that people maybe would vary their acceleration by, for example, 1 meter per second. And that's going to be your variance. For example, you put that in the diagonal. Okay. So now after doing this, we have Q as this matrix. Notice that Q now changes with K, because T sub K is not a constant. You know why? Because if we assume that we have a fixed sampling rate, like every 1 second or every 0.1 second we get a location measurement, then this K here would be dropped. This is the time step. Okay. But like, for example, when you consider the problem of an occupant walking in a building and we capture their vibration through accelerometers, so we generate an estimate of the location every time someone stomps on the floor, every time there's a footstep. And the time between 2 consecutive footsteps could be not uniform. Okay. So, okay, we have now a measurement model. It's F times X K minus 1 plus W here. And W, we have its covariance here. Okay. Then in this case, my measurements, what am I measuring? I'm measuring some linear combination of x, right? But notice here what I'm doing. I'm taking the measurements, the observations are nothing but the first, the second state, and the final state, which are x and y. So position, the location. So I'm doing some magic, okay, and I'm coming up with a location measurement. It could be that I'm using a LiDAR system to get the location of the occupant. It could be that I'm using some smart algorithm that uses the accelerometer data to measure location. But what my measurement system is giving me is just location, the x and y coordinates. So x and y coordinates are nothing but the first and the last, the second and the last elements in the state vector here, x and y. So in order to extract them, we just come up with this h. Notice that h here is time invariant. So again, these matrices, the parameters h, f, b, q, and r, they could be time varying or time invariant depending on the problem that you're dealing with. For this specific example, h is time invariant, but you saw that q is time varying, f is time varying. Now here r, we want to come up with r, which is, this is what I call e here. We called it v in the presentation. This is the additive noise to our measurement system. It could be, this additive noise could be for example, could capture sensor noise. It could capture inaccuracies in our modeling abilities, because we have an algorithm that converts maybe vibration or a laser signal to location. And so that might be the algorithm that converts that to location might have a model in there, could be nonlinear model, and maybe that model is not accurate. So anyways, we have to assume that this guy is zero mean, white noise, and we have to come up with the covariance of it. So notice the covariance here adds, we're going to assume that the covariance is some diagonal element. And these diagonal elements, this is the covariance of the noise V. These diagonal elements, I call them sigma sub x, sigma sub y. Why is that? They capture the uncertainty about my measurement system when it comes to measuring the x and the y coordinates. So if for some reason I know for sure that my measurement system that is giving me the location has high uncertainty in the x, then sigma, and then this first component must be higher than the second component. Yeah, but I mean, I put them as uniformly. Actually, I did take that into account. I took into account the fact that, so I did, and I don't know if we have it here. Exactly. So notice here, this is the instrumented area that we used, and it's like a narrow rectangular area. So you have a longer distance in the x direction than the distance in the y direction if you put like a rectangle on the instrumented area. So I incorporated that. Yes, I did. So, but no. I did some trials by myself, but I mean the improvement wasn't great, mainly because in this case the measurement model had high uncertainty. Yeah. Yeah. Yeah, I mean, there are papers that talk about how to initialize the Kalman filter and how to estimate a more representative covariance matrices, the R and Q matrices. So we have now a measurement model. We derived a state model. We just apply the equations here, and that's it. Yeah, there was an improvement. Yeah, there was an improvement. Did I highlight it? Yeah. Where reduction, localization, error reduction after using the Kalman filter. There's a percentage. There's a 16.7% overall reduction in the error after using the Kalman filter. Comparing between just getting the measurements without using the state model, and compare that to the Kalman filter, which fuses the state model to the measurement model, we got an improvement. It basically says, for example, the Kalman filter, what it does, if you have someone walking, like these are the legs of someone walking. One step, you have the first measurement here, you have the second measurement here. If the third measurement comes out here, then the Kalman filter would say, oh, wait a minute, but I have a state model that says that if you have two footsteps here and here, then the third one should be here. Then, but you're telling me that the next measurement is too far, then the Kalman filter incorporates or fuses the prediction from the state model to the measurement, and then you get the well, here it depends on what your R and Q matrices are. Yeah, because this is how this is how the weighting takes place. So if your measurements, so if your measurement system is really accurate, but you want to improve it slightly with the prediction with the state model, then you would have high confidence in your measurement model. So mainly your Kalman filter would rely on the measurement more. Or it could be the other way. You have measurement model that sucks, has high uncertainty. Then you want to rely more on your prediction. The way things were derived in this presentation, it's based on reference one if you want to know the details. But basically, we have a quadratic function. We take the derivative, set that equal to 0. It's a nice way of, and actually, the way we derive the Kalman filter here, it's an optimal filter regardless whether we have Gaussian additive white noise or not, which is an interesting thing because if you derive the Kalman filter in a Bayesian approach, which I'm not going to show here, I did not show, then it will only be the optimal solution if the noise is only Gaussian. In case, God forbid, you want to get to the Bayesian derivation of the Kalman filter, you need these pointers. You need to know what a Markov process is, which is not tough, but like these tools I give in this slide, I'm not gonna spend time because we run out of time. These tools will help you derive the Kalman filter in a Bayesian approach. We don't have the time for that, and I don't think you guys have the bandwidth, even if we have time to comprehend that. But basically, you've seen that in order to derive, now here I'm talking about deriving the Kalman filter, you need to have strong knowledge in probability theory, and you also need to have good knowledge of linear algebra, because remember these objective functions, matrix calculus, optimization theory, because we have a cost function, we want to minimize it, and to be able to derive it yourself, the Kalman filter, or understand the derivation, you need to also have not only fundamental knowledge in the previous fields, but also have knowledge of some theorems and identities. Without that, you're gonna spend a lot of time just going in circles. In my opinion, for non-math and non-stats majors, learning and teaching the Kalman filter is hard. If you want to understand the details, I don't like to learn something. If someone gives me an equation and ask me, hey, this is the Kalman filter, like the slide I showed earlier. Oh, you want to implement the Kalman filter? Just do this. That makes me angry. But at the same time, I've given you a lot of information. I don't expect you to, to comprehend everything, because we covered a lot of stuff. Sometimes we did not give enough examples. But at least I'm hoping that I've given you high level knowledge plus some tools that if you want to go and study this on your own or derive the Kalman filter, at least you have a great head start. These are the main references that I used in this presentation. Okay, I'm going to stop here.